Corey Harris here. Thank you for tuning into the Out of Office channel. So a couple of things I want to address. I first want to thank the community for being patient. So I know I had previously planned to create the AI and ML study guide and even take the certification. Unfortunately, life events has prevented that from happening. So shortly after Out of Office was released, I began to mourn the loss of my grandfather, Elmer Coppers Sr. He passed January the 30th, 2022. Shortly after he passed, my other grandfather, Lewis A. Harris Sr., he passed February 26th, 2022. I've been heavily focused with my family, and I've been heavily focused in maintaining the cadence with my current employment at AWS. And so let's get to the video. Corey Harris here. So today we're going to talk about operating AWS Lambda, and specifically we're going to dive into the Lambda Lifecycle. Serverless is very advantageous for developers. It is a managed service and it requires no administering of infrastructure. Now the question becomes, how does it work? So this will allow you to understand more about how the Lambda service orchestrates and invokes and maintains Lambda functions. We're going to start by giving the overview of the Lambda lifecycle, and we'll also dive into the 3 phases of the lifecycle. We'll then talk about the cold starts and making sure we understand the conditions and when they happen. And we'll also talk about provision concurrency and how that can alleviate the cold start problem. And then we'll go into different invocation patterns of your Lambda handler. So there are synchronous handlers and there are asynchronous handlers, and they both operate very differently. And understanding the different invocation patterns can enable you to make fit for purpose APIs and not blindly leverage one over the other. So let's dive right into the Lambda lifecycle. Well, when Lambda gets a request, the Lambda service goes to prepare an execution environment for that particular Lambda function. And as a part of preparing that environment, it has to first download the code artifacts from an S3 bucket. Now, it might also be ECR if you are using the containerized packaging option for your Lambda function. Next, it creates the execution environment, and it also configures the memory, the runtime, and all of the function configurations that were specified. And because we don't allow customers to allocate CPU, we'll automatically assign you appropriate CPU based on the memory that you select. Lambda will run the initialization code that is outside of the event handler before finally running the event handler itself. And then this brings us to the 3 phases of the life cycle. So let's dive into the init phase. Now in the init phase, Lambda will perform 3 different tasks. The first task is that it will start all extensions, and this is the extension init. Now there are 2 types of extensions. There are internal extensions and there are external extensions. The internal extensions run in the function runtime, and external extensions sit outside the function runtime while within the execution environment. And extensions were created to give customers the ability to deeply integrate with the Lambda service. Use cases for extensions are fetching configuration values or fetching secrets. What this does is now you can build that logic outside of your function code, but it runs as a layer in your function, and you can build once and deploy everywhere. Also do things like instrument your code without changing anything on the application side. You still have access to the execution environment when leveraging an extension. The next thing that happens is the Lambda service will bootstrap the runtime, and this is called the runtime init. And then it will run the function static code. So again, this is the code that sits above the event handler. And this initializes the actual function. This is a common place where customers will do things such as creating your clients or initializing all of the configuration variables that you may be leveraging within the function, or grabbing any downstream endpoints that you need to use within that function. Typically those values will get initialized in the init, and within the handler you would just check to see if those values are still defined. But we'll talk more about that later as well. Now the init phase ends when the runtime and all registered extensions signal that they are ready by sending a next API request. Now this process is limited to 10 seconds. Now if all 3 of these do not finish in 10 seconds, the Lambda will retry the init at the next time of a function invocation. All right, so earlier we talked about how the function init has to complete within 10 seconds or the Lambda service will reattempt the function init at the next invocation. And if it fails again, then the function will permanently fail. So let's test that out to see what we would deem expected behavior. So here I created a function, and this function sets a variable cold start to true because everything above line 20 is in the init. So this would signify that it had to be a cold start because it executed this line of code. I've prefixed all messages to locate where they're being printed from. So these are messages coming from the init, and it's basically just saying this function is located in the function init and signifies the function has experienced a cold start. And I'm also gonna make a variable called 0 because I wanna see when this variable gets updated. And I'm gonna make a function called chillout, and it's nothing but a promise wrapper for an anonymous function that is going to set an 11-second timeout on running this command. So all this function is doing is it's gonna print this line of code after 11 seconds. And I'm going to set this variable equal to that promise that is getting returned here. And then I'm gonna run a .then, meaning after this promise is resolved, I wanna print this line, and I want to change the value of sample, and I want to see what that value is, and I want to see when this gets printed. Then I'll go down to my handler, and I'm going to say if the cold start is true, then after this promise is resolved, I want to print that I waited in the handler for the sample value of sample, and we'll see what that value is. Then we'll set cold start to false, and then we'll return a new promise, which is going to say this is a cold start and we exited at the top of the function handler, and here's the value that I had at the time of the exit. Now, if the function is not a cold start, meaning the second invocation, this will have been made false, and then the function will skip this block and it will come down here and it will just make a 200 response. Is going to set handler to true so that I know that this was in the handler, and then it's going to just tell me the value of cold start. I'm going to return that as a promise because I have an asynchronous handler. But the goal here is that we want to understand what's going to happen. What do you think is going to happen? I have a timeout in my function init, and I'm actually resolving that promise in my init. So this function is going to run in 11 seconds. So conceptually, you would think that, well, the function init should break because it's gonna wait for 11 seconds before it's done. So let's see what happens. Okay, so let's look at this. We got a response and it said from the handler, this is a cold start, and we exited at the top of the function handler. And the value is 0. And we also see a couple things. We see a request ID here. Right? I want you to pay close attention to this request ID and look at the prefix 4C82. Just keep that in your mind, 4C82. Now you see the init is ran and it says this function is located in the function init. It signifies that we've experienced a cold start. And we also see the line in which we're specifying that we're setting an 11-second timeout. But this function returned in a second, right? This function returned in 15 milliseconds. Well, the init duration plus this, about 170 milliseconds. So why didn't it wait 11 seconds, right? What happened to the line of code here? In my function init, I said, hey, I want you to resolve this promise and I want you to print this thing out. And yet we don't see anything on the execution results, okay? So let's see what happens when I run this a second time. Wow, okay. So let's look at this. So now cold start is false. So it was a warm start. But here's the interesting piece. If you remember, I said pay close attention to the prefix of that request ID, right? Because now we see it here. But then look here, there's a new request ID. So what does this mean? Function init is not going to wait for asynchronous events to be processed. And this goes back to core JavaScript event loop practices. When you use callbacks or promises, those requests are not processed immediately. They're put on the event queue. And so what happens is JavaScript will put the request on the event queue and it will immediately execute the next line of code. So that's what happened here. That's why you have a situation where these two actually came after the invocation, where we saw the handler return in the previous invocation, right? We saw the handler return and we saw this line of code in the first execution, right? But in the second execution, we saw this one. And you would think, well, this happens before this one. So how is it that we saw this first and we didn't see this until the second invocation? The function init process in Lambda was technically finished. So remember, this is expected behavior. So even though we configured an 11-second timeout, because of the way JavaScript works, the function init was finished its job, right? It had nothing else to process because, again, remember, callbacks and promises are put on the event queue. They're not processed synchronously. And so JavaScript is going to just push that request on the event queue and go right to the next line of code. So when it hit this part of the code, it put the fact that I need to resolve this promise and set this to 99999 and then print this. But before I do that, I need to go process this, and I'm gonna put this on the queue, and I'm gonna come process that later. And that's exactly what happened. So that's why we were able to still see this get printed and the value is 0, because the init was technically completed. So the function will return. It said, I'm done. I put everything on the event loop. It is your job as a developer to make sure there are no hanging threads between invocations. So this would be considered a bad practice. This example was only created to outline the function init, not to say this is how you should create promises. But I wanted to be able to show you in practice how the function init actually works, right? So let's try something. So let's see if we can understand how to get the function init to actually wait before something is done before it returns. So let's do something like this. While true equals nothing, just while true. Now, what do you think will happen here? Let's just take a look. So now you can see that the function init is not able to return. And why is that? The reason is because a while loop or a for loop are synchronously completed. JavaScript will process that line of code at the time that it gets there. It doesn't put it on the event queue. So the moral here is the only thing that can keep the function init hung is if you have an IO blocking call that you're making in JavaScript or Node.js in this example. So we talked about the function init. We also demoed how the function init works so that we could properly assess expected behavior. So in the invoke phase for a Lambda function, when a Lambda function is invoked in response to a next API request, Lambda is going to send the event to the runtime and each extension. So for customers looking to build extensions or understanding how extensions can provide that level of flexibility, it has access to the same resources and information as the function itself. So this really allows you to build fit for purpose layers in your application that you can reuse across multiple functions. Now the function timeout setting limits the duration of the entire invoke phase. So all of my extensions have to respond in time with the function timeout. There is no separation between the three. So very important to monitor the performance of your extensions. Now the invoke phase ends by sending a next API request, and then it will be ready for another invocation. So what happens if Lambda crashes? What if the function has an error or it times out? Or what happens to the execution environment in that case? So when that happens, the Lambda service will behave like a shutdown event. And the Lambda service will shut down the runtime. It will send shutdown event signal to each registered external extension. And then if another invoke results in the environment being reused, Lambda initializes the extensions and runtime as a part of the next invocation. So as you can see, it looks very similar to an init. So in this process, you will experience a cold start because technically the environment is recreating itself. Now, again, the caveat here is that is only if the invoke results in that specific environment being reused again. The Lambda service may choose a different environment that may not have been shut down. So let's talk about the shutdown lifecycle phase, which is pretty straightforward. So Lambda will send a shutdown event to the runtime in each external extension. So very similar to what you saw in the invoke with error phase. And even on the image below, you can see the similarities between shutdown and the invoke with error. The duration of the shutdown is capped at 2 seconds. Lambda will execute a sig kill if the extensions do not respond in time. So it's very important that if you have any extensions that are still going to run after the function is completed, that you ensure that they are done within 2 seconds so there are no loose processes within your application. So reusing the execution environment for Lambda has the following implications. So the first thing is that objects declared outside the handler will remain initialized. So for example, database connections, right? A lot of customers implement what we call pooling, where you will create a database connection and you'll reuse it across multiple invocations. The reason that customers do that is because databases typically have a connection maximum limit, as well as the process to set up those connections adds latency to the application. In order to prevent throttling your database and setting up a new connection every time you invoke the function, and then also adding that latency of setting up that connection, we recommend database connection pooling. The next thing is each execution provides 512 megabytes of disk space in the /temp. So this can act as a transient cache, and it is not against best practices to leverage it as a cache. The only caveat is that if you choose to leverage it as a cache, you have to ensure the cache is defined before assuming to use any of the variables in the cache. And the next thing is background processes or callbacks that were initialized by your Lambda and did not complete will resume if Lambda reuses that environment. Now, this is something that we proved earlier, right? Because in the example demo, you saw a request ID with a certain prefix, and you saw that there was a promise that was resolved that didn't show up in the console logs. However, when we re-executed that same function seconds later, we proved that it wasn't a cold start because the variable was now false. And then we saw the old request ID in the middle of the new request ID block, which signifies that the Lambda service indeed caught all of those hanging threads and allowed us to see them on the next invocations. This is not a best practice. You want to ensure that all of your threads are caught before the function is shut down. So we talked about the Lambda lifecycle, and we dove into the init phase. We dove into a demo showing how the function init works and what is expected behavior. Now, we also talked about the invoke phase and how Lambda processes events and how Lambda responds to failed invocations, right? And what happens to the runtime when that occurs. And then we talked about what happens during the shutdown. So now let's talk about cold starts and make sure that we understand when they occur. And then we'll talk more about how we can mitigate these from occurring. So, cold starts. I want to first preface by saying Lambda is a highly available service that manages execution across multiple availability zones in an AWS region. That is imperative to remember. Just because your function is invoked does not mean that it is invoked in the same availability zone, right? It might be in a separate availability zone next time. And that's important to know as we move along in the cold start discussion. So when does a cold start happen? Well, we know it happens when a function is first created. So because we know it happens when the function is created, then it's implied that it also happens when the function is updated, because technically that's going to be a net new deploy. Updating a function configuration. So let's say I have a Lambda function and it has an IAM role that's attached to it, but it doesn't have enough access. And I know this because my log said that I got an unauthorized exception. And so I go into the IAM console and I add a policy to that role that I'm using for Lambda. What happens there? This is a warm start. The reason is because the environment for Lambda has remained the same. The ARN that Lambda is relying on for its role definition has not changed. So all I have done is just added permissions to a role that is still the same from a Lambda standpoint. Let's look at this, for example. So let's say you have environment variables hard-coded in Lambda, and then you also have another process for your other function that uses AWS app config to pull the configuration parameters from the app config service itself during the function init. And let's say you want to update the configuration variables in both contexts. Which one would mandate a cold start? The environment variables would get a cold start because that changes the Lambda environment itself, so it has to rebuild. Now, app config, because you're relying on asynchronous calls to hydrate your configuration variables, you would just make the changes in the AWS app config context, and Lambda would pick up whatever changes those were. So this is a good way to reduce the dependency to redeploy a function when you make certain changes. So in the open source community, to solve the cold start problem, it's been very common that they will leverage Event Bridge. These libraries will leverage Event Bridge. And what happens is they'll ping a Lambda function, for example. And ideally, you would think that that would keep a function warm because it would have steady traffic. And so the Lambda service would not shut down that actual instance of Lambda because it was active. It was taking requests. However, it depends. It is not always certain that if you ping or use these libraries that your function will never experience a cold start. So one reason could be there may not be enough instances of the function once a request hits the Lambda service. Also, when traffic is being load balanced internally due to aggregate customer traffic. So this is a big one. Remember, Lambda is a highly available service that manages executions across multiple availability zones. And so in order to maintain the integrity of Lambda and allow customers to scale as gracefully as they have been, we need to ensure that the spread of traffic across a region is up to par. And so if they sense that it needs to be load balanced to properly distribute traffic so that there is no bottlenecks or no single points of failure, then it will attempt to load balance a Lambda from one availability zone to the next. Now, this Lambda could have been heavily used. It could be something that customers are using all the time. But if that event is triggered, then that function will be reaped. That environment will be reaped and it will be rebuilt in a separate availability zone, and you will experience a cold start even though you have given the function steady traffic. That's where provision concurrency comes into play. So provision concurrency is a way for customers to ensure that their code and their Lambda function has already passed function init and is ready for invocation. So how do we do that? So for every 1 unit of provision concurrency, a minimum of 2 execution environments in separate availability zones will be created. So this is how we're able to manage the fact that if you get load balanced, we'll still have extra copies of your function that have already been initialized. Your logging may get more verbose because you will see the activity of the Lambda service initializing your function over and over and over again. So just keep that in mind. And provision concurrency only works with published versions of a function, not with the $latest alias. I want to touch on invocation patterns just to make sure that everyone is aware on how this may impact performance and also your ability to process messages at scale. So let's look at simultaneous requests. So let's imagine that there's an application that you have and it's highly concurrent, right? It has 6 requests at a time. And let's assume that at this point, your Lambda allocation is 0. So you don't have any available instances of a Lambda function. What happens in this scenario is that you're going to get 6 cold starts. for as long as your handler is synchronous, right? So if I have an API gateway that sits in front of a Lambda function, and I have a synchronous handler, and I submit 6 API calls, I'm going to get 6 different Lambda environments that get created because they all came in at the exact same time. And so as you can see here, all your functions will share a cold start, and then they'll go into invocation. Is this a bad thing? Absolutely not. This might be exactly what you expect, but it's important to note how it's happening and why. Let's look at this invocation pattern with 6 requests, but they have a staggered arrival. So when you look at this, you can see that there's already some inherent environmental reuse in play here. And this is the power of asynchronous handlers. So what happens is when the request hits the Lambda service, it'll first look at the first message that it received and say, hey, I don't have a resource ready for this. I have to make one, and I'll process. Now, mid-invocation, the second event is going to hit the Lambda service and say, hey, I need to get processed too. And then the Lambda service will say, well, I don't have an environment for you either, so I have to make one. So then you have a second one. But then when the third one comes in the queue, right, the first environment's done. So Lambda says, hey, I have an environment you can use. And then the same happens to the 4th, 5th, and 6th, respectively. So this is a scenario where you've implemented inherent environmental reuse by using asynchronous style handlers. But in this case, the only guarantee is that you'll have one cold start. The others vary based on the completion time of the previous instances of Lambda. So again, is it a bad thing? Absolutely not. But it's important to know why this is happening. So how does this asynchronous pattern with Lambda work? So for asynchronous invocations, an internal queue sits in between the caller and the Lambda service. And so the event gets placed on a queue, and Lambda will process the event after it gets on the queue. So if I was to make 10 simultaneous requests, inherently they would all be staggered because they're all going to get written to an internal queue that Lambda is going to process off of. So naturally, you're going to eliminate how many requests you get at the same exact time. And just making a switch like that can reduce your need for concurrency, as you saw in the previous graphic. Another thing to note here is that the service-to-service integrations that we implement within the platform are more often than not asynchronous. So for example, when you want to configure a Lambda to be triggered after a post to an S3 bucket, that interaction between S3 and Lambda is asynchronous. So I want to thank you all for tuning in to the Lambda Lifecycle video. Stay tuned for more updates.